Ooh. Can I just turn this into you?
Is that homework? Yeah, you can put a pile there. Thanks. Test, test, test. Mic check. Let's see. Test, test, test. Which mic is it using? Oh, no, those are for you to keep. So yeah, I just need your homework. Oh, somebody put no name on their homework, just turn it in. All right. Sorry about that. Between printer difficulties and technical difficulties, running a tad late. All right, so last week we were talking about how to classify substances. So we kind of got, at least we started to get a feel for that. So what's an element, what's a compound, what's a mixture, so all those sorts of things. So chapter 2, we're just going to be diving deeper into that. So we'll take a deeper look at the periodic table and all the properties. So like we went over last week, so an element is a pure substance that cannot be broken down. And so if it cannot be broken down into smaller atoms, then that means it has to be an element, so it has to be something on our periodic table. So all of these are fundamental building blocks. So anything from little hydrogen, and then we start getting to these elements, all these are synthetic. And I think this periodic table is a little outdated because they have some names for some of these funny ones now. And so, of course, elements are also important. That's what's in our human body. So our body is made up of mainly 65% oxygen, but of course we're carbon-based life forms, so we also have a lot of carbon, so 18% carbon, 10% hydrogen, 3% nitrogen. And then of course we have all sorts of other little metals in our body, from iron in our hemoglobin, and then other elements are also essential, so manganese, chromium, and all these are essential in just small amounts. And so you can see what else is present in the human body. So of course, calcium, phosphorus, potassium, sulfur, sodium, chlorine. We have all these ions in our body. enzymes are also comprised, right? They have elements in them to make your big enzymes, and then of course small percentage. And so meanwhile, compounds are going to be 2 or more atoms. And again, a compound will have a defined chemical formula. And so unlike some of those mixtures, so remember we mentioned brass, that was part of our mixtures last week. So brass, right, that would not be a compound because you can change the ratio of copper to zinc and so forth. So it's not a defined ratio, unlike, sodium chloride or, quartz or silicon dioxide. So all those, right, have a defined chemical formula. They're always going to be bound like that. So you're not going to have a different ratio. And if you do, it's a different compound. So we mentioned, right, we could have NO, NO2, N2O3. All those would be different, distinct compounds. And then we also want to start familiarizing ourselves with what they're going to look like, the different 3D representations. So this is kind of our sphere model. And so this is just water. So usually the red represents oxygen. So there's our nice big red ball for oxygen. And then whites are always hydrogen. And so we could just rewrite this like so. And of course, this is showing us the geometry. So this is what water looks like in the 3D form. It has a bent structure. And later, we'll look at why. So we could go ahead and add our lone pairs. But we don't really know what this means right now. So I'm just kind of showing you, but we'll get there. And then, so this is another kind of ball and stick model representation. And so these black balls, so black always represents carbon. So this is carbon and hydrogen. So I'll translate that. Carbon, carbon. And we can add our hydrogens on there. So this is what this means. You could also write it, and we won't see this as much, but I'll just make you aware of it. So you also have a shorthand where you could just draw that, and that would be ethane as well. So this is like organic chemistry shorthand. So each point represents a carbon, and then they don't show you the hydrogens explicitly, and we'll get used to looking at kind of OChem structures. But this means the same thing as that structure. Kind of funky there. And so again, this is just another way to represent our molecules. So now this is kind of more the organic chemistry method, and by that I mean they do not label your carbons. So any point here, that's a carbon. So carbon, 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 carbon. And then the other thing is, like I mentioned on this representation, we don't show the hydrogens. And so same thing on here. So the hydrogens are not shown. And so let's go over this together. Let's kind of rewrite it. And so the other thing you want to be able to do is, can you look at a molecule and determine its formula? And so let's kind of rewrite this. So I have an oxygen. These two lines represent double bonds. And then, so this point's a carbon. So I'm just going to explicitly write a carbon there. Nitrogen. So this would be a carbon. So that's that point, carbon. Nitrogen. So this group is called a methyl group here. And all that is a carbon with 3 hydrogens attached to it. So carbon. So there's our nitrogen. So I'm just building up our 5-membered ring there. And so now let's continue. So now we're back on this side. So we have another methyl group. Draw it explicitly. Nitrogen. So there's another carbon. So that's this joint right here. Oxygen. Nitrogen. Our other methyl group. So I'll just write CH3. And then last, our final carbon there. And so this is jumping ahead for a second, but we'll get to why later. But carbon needs 4 bonds. And so that's why I went ahead, and again, in OCHEM, we don't show hydrogen, so anywhere that carbon didn't have 4 bonds, I need to add a hydrogen to it. And now everywhere else, carbon should be satisfied, but I'm just double checking that we didn't leave any stragglers, so I don't have to add any hydrogens anywhere. But 4 bonds, 4 bonds, 4 bonds, 4 bonds. Okay, that looks all good. So this is our now explicit structure. So all we've done is we translated this standard OCHEM structure to now a more explicitly drawn structure with our carbons and our hydrogens. And so now we can come up with our formula. And so the traditional way of doing your formula for like an organic molecule is you do carbon, hydrogen, nitrogen, and then oxygen, and then the other elements. And so let's fill in our subscripts to indicate how many there are. So count up the carbons. How many carbons do you see? So give everyone a minute. Oh, and I might have forgotten some explicitly. So that was a carbon. So 1, 2, 3, 4, 5, 6, 7, 8. Is that what people got? 8 carbons? 1, 2, 3, 4, 5, 6, 7, 8. Do y'all get 8? Some thumbs up, some nods. All right, so C8, H. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So H9, N. So we have 1, 2, 3, 4 nitrogens and 2 oxygens. And so that's our formula. So C8, H9, N4, O2. And again, that's our defined chemical formula. So that means this is a compound, and it's always going to be this formula because that is always what your individual molecule looks like. Let's do another practice. We'll do 2 similar but different examples. And so now let's compare this versus this drawing. And so just looking at it, so again, recognize this is an organic chemistry structure. Each one of these points is a carbon, and then anything not filled in, if it doesn't have 4 bonds, we need to add a hydrogen. So now I'll redraw kind of the explicit format. So carbon, 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 so everything's a carbon. So we should have 6 carbons. And now they currently have 2 bonds, 1, 2. So I'm going to fill in a hydrogen on each of those carbons. So what's our formula for this first structure? C. So 6 carbons, and then how many hydrogens? So C6H12. Excellent job. And then for this one, so notice it has all these double bonds. Sometimes you may also see this same molecule drawn like this, and that just means it has the same thing, delocalized pi bonds all across. But what you need to recognize is, again, how to translate that into a formula. So in this case, we have carbon, carbon, and we'll put a double bond there. This one skips it, carbon. Now we have a double bond, so that's just translating this structure. Single bond. So now I've just translated this without my hydrogens. So notice 3 double bonds, 3 double bonds. And we'd add in our hydrogens so that each carbon has 4 bonds total. And so what's the formula for this molecule? So C6H6. Very good. And then so just so you know what these would be called in the real world. So this one is going to be called cyclohexane. And so just so we can look at the naming. So cyclo, meaning we have a circle structure, so some sort of ring. Hexane, so hex stands for 6. So 6 carbons in a ring. And then this one has a special name, so this one is called benzene. And you may have heard of benzene before, so it's a really common solvent. It is carcinogenic, though, but back in the good old days of chemistry, after you were done, you did your experiment at the end of the day, you did a good old benzene dip to wash your hands off. So now we don't do that. We learned it was carcinogenic. Oops. But that's how things go. All right. So now let's kind of start with our atomic structure, kind of getting to how we build the periodic table. So our atomic structure, so atoms are all composed of the same subatomic particles. So atoms are all made out of protons, neutrons, and electrons. And so let's, oops, can't add a picture there. And so that means, so let's kind of look at our elementary school depiction of an atom. So we have our nucleus in the center. And so the nucleus is made up of the protons plus neutrons. And the protons we'll see are positively charged formally. And the nucleus is also where all the mass is. And we'll see what I mean by that as we look into the exact numbers. And then around, so floating around the nucleus and this electron cloud is going to be your electrons. And so we'll look more at the structure and shape of these actual electronic clouds and as we go into the chapter. But we'll take, again, an elementary school kind of look. Just the electrons are surrounding the nucleus. And so electrons are also going to have a formally negative charge and essentially massless. And so if we look at here, so protons and neutrons have nearly identical masses. And so the mass of a proton is 1.67. The rest of this doesn't really matter, times 10 to the negative 27 kilograms. Neutron is about the same, 1.67 times 10 to the negative 27. And then, oh, look at your electron. So 9.1 times 10 to the negative 31. So anytime we're talking about adding our masses together, we're just going to be looking at the numbers of protons plus neutrons. And that's going to give us that mass for that individual atom. And you can tell kind of with your sig figs, right, if you were to add that up and line that up, the electron is not significant. That's why we just go ahead and ignore its mass. And then the charge of the proton and the charge of the electron are equal in magnitude, but opposite in sign. And so the neutron, of course, has no charge. It was a little elusive. And so this is a good chart that gives us a summary. And so we have a special unit of mass, especially when we're talking about individual atoms. So that's going to be the AMU, or atomic mass unit. And you can just assume that a proton is 1 AMU, a neutron is 1 AMU, and again, electron, if you look at that, so 0.00055, so again, negligible. Then we have our charge. So again, our electron is negatively charged, proton is positively charged, and that is equal to 1.6 times 10 to the negative 19 coulombs. And so the most important thing, so star it, whatever you need to do. So elements are defined by their number of protons. And so if you look at the periodic table, you look at your periodic table, if this has a 1 here, that's how many protons it has. So whatever number is in this corner corresponds to the number of protons. And so it should say that this is its atomic number, but the atomic number is just the same thing as the number of protons. And so if you change the number of protons, you've completely changed the element. And that happens, right, in nuclear reactions. So you could have that happening. Obviously, it doesn't commonly happen. But again, you change the protons, you change the element. So just keep starring that, whatever. And so the number of protons in an atom's nucleus is its atomic number and is given by the symbol Z. So if you need to put that somewhere, okay, so protons, that's just Z formally, again, is just going to correspond to that number on the periodic table. So let's zoom in on this little picture here. So at helium, if we're looking at our nucleus, and it's pointing, so the red is shown here to indicate our number of protons. So it has 2. They're not showing us, or they're not pointing it out, but we can see that it has 2 other balls here, so that those are going to be the neutrons. And so if we look, helium, 2 protons, so its atomic number should be 2. Yes, that makes sense. And then we'll talk about the discrepancies in mass later. But we know that helium should be 4, and that's where our mass comes in. So our mass then is going to be 2 protons plus 2 neutrons, so we have 4 total for our mass. Now we're looking at carbon over here. So 1, 2, 3, 4, 5, 6. 6 protons in the nucleus. We can go back to our periodic table. 6, so carbon's element 6. And then we can count up our neutrons. So 1, 2, 3, 4, 5, 6. So this also happens to have 6 neutrons as well. And so I know for this carbon, its mass is again going to be 6 protons plus 6 neutrons, so giving us 12 AMU. And so if we look at our periodic table, they are arranged in increasing atomic number. And so we see that, again, let's go back to this one. So we go 1. We'll explain why 2's over here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you see that they go in order, but they are in kind of a funny arrangement, right? So we don't just run the periodic table across. We don't have just arbitrary cuts. So they're arranged like this due to a reason. And so elements are represented in the periodic table by their symbol and atomic number. And so you have their chemical symbol here, and it should have the name, so you can look at your periodic table. It probably has a key that's slightly different. So again, atomic number, name, then we have some sort of mass. And this atomic mass is going to be the average of the isotopes, but let's save that conversation for right now. So isotopes are elements with varied numbers of neutrons. And so all atoms of a given element have the same number of protons. So again, let's repeat that. Atoms of a given element have the same number of protons. However, they may have different neutrons. And so they're going to talk about neon, but let's look at carbon. So you may be familiar with carbon. So does anybody know what the other isotopes of carbon are? So we know carbon-12. So this is carbon-12, that's the example we looked at up here. So that's kind of our most common isotope. And then what are the other ones? Or maybe what would they be used for? Have you heard of them in some sense? And I'll put on some numbers here. So this is about 98.84% abundance. And then the next useful isotope, or at least I think this is useful. So we have carbon-13. And so this is rare, or rarer. So it's only about 1% of the isotopes. And why it's relevant is it's good for carbon NMR. So I won't go into the details of why you have to use carbon-13, but basically carbon-13 is the only NMR active nucleus. And so an NMR is basically a huge magnet essentially. So it takes your little compound, it sends a magnetic field, it lines up all the electrons, there is a relaxation, and the point is it makes a pretty picture so you can tell what the heck you have. But this is a common technique that's used like in organic chemistry to look at and characterize whatever you made. And so this is important. This is also a stable isotope. So again, low abundance, but very important. And then anyone remember what carbon's used for? So carbon-14 is used for carbon dating. Yeah, let's see, what's the... So this is 1 part per trillion. So that's really small. So very small abundance. And so this is not stable. And it has a half-life of 5,700 years or so. And it is used for carbon dating. And so what you do is you know the abundance of carbon and its ratio just normally, so it has a specific ratio, and that's based on, you know, your natural abundance. And then once you die, you're no longer incorporating, you know, carbon into you. And so that means that that carbon-14 in that specimen is going to start decaying. So you're going to have an even smaller amount of carbon-14. And so you can look at the ratio of your specimen of carbon-14 to 12, compare it to now of 14 to 12, and then you can get a date. And so that's how they do dating for all the fossils and trees and things that they find, is as long as it's not too old, because again, notice, right, it only has a half-life of 5,000 years, so it can only go back so far, but it's useful for doing relatively recent dating. And so now let's talk about, so what does it mean when we have carbon-12, carbon-13, carbon-14? Well, we just finished saying that if it's carbon, it has to have 6 protons. And so we'll go protons, neutrons, electrons. So carbon 12, so they all have 6 protons. Notice that this number refers to the total mass, so that's why it's there. And so how many neutrons did our carbon 12 have then? 6. And then, so we haven't quite gone over this yet, but we know for a neutral compound, our protons have to equal our number of electrons. So how many electrons would this have? 6. And then, so let's try carbon 13 then. How many neutrons does carbon 13 have? So 7, exactly. So 7 plus 6 gives you 13. And then how many electrons? So still 6, good. Don't let anything trick you. And then so carbon 14, how many neutrons would it have? 8, excellent. So 6 plus 8, that's how we get our 14. And then how many electrons? 6, good. I'm sorry, I have allergies, not COVID or anything. I just always cough. Coughing's illegal now. And so looking at neon, and so different elements can have different number of isotopes. And if you're ever bored in the lab one day, there's a whole isotope chart, like near where the fish tank is. So you could stare at it, look at all the abundances, so look at all the different isotopes. But again, so what we can get from this representation, we have neon 20, neon 21, neon 22. And so we can look, so this is the atomic number down there. So this is just another representation. So we could have written carbon in the same manner, so 12, carbon, 6. So same thing, 13, carbon, 6, 14, carbon, 6, yeah.
I'm a little bit confused when they're talking about subscript and superscript and how that applies to that.
So I would have to look like exactly in the book what you're talking about, but so you use mainly just subscripts when we're writing our formulas. And this is kind of just different forms for representing our atom. And so you could write it as either like neon 20, like that, and I wouldn't have to write this 10 here. It's just this 10 is trying to help you and be explicit and show you your atomic number. So you could write it in this form, where it's kind of a little superscript over a subscript, 20 over 10. You could leave out that atomic number. People should still know what that means. I don't know if that clarified your question. You could also write it, you know, sometimes you just see like 20 neon or something like that, 13 carbon. So you could see it in different forms like that. But kind of the key thing when writing it in this form is your upper number should be your total mass. So if you're looking at something, you should see, you know, what's my total mass? If you're unsure, like let's say you were looking at this neon symbol and like, I don't really know what's going on. I got a little confused. Well, if you go back to your periodic table, just look up neon, and then, oh, okay, that 10 probably means it's the atomic number, and it's right there. It's 10. You can remind yourself, okay, that's how many protons there are, and kind of reorient yourself.
So, like when you have isotopes and then you're looking at the element on the table, they're kind of like swapped. Like atomic mass is
Yeah.
where the atomic number is. They're like backwards almost. Or maybe I'm just reading it wrong.
I see what you mean, where like the numbers on top, like, yeah, the mass number's on top when we write the symbol, but yeah, the periodic table has it on bottom. And then going back to kind of the isotope conversation, and we'll do some more math with this later, but why the mass is 12.011, it's because you have mainly carbon 12, so that gives you your main number of 12, but then it has that 0.011 because you have some abundance of 13, some tiny abundance of 14. So the mass here is really your average mass. So if you were to weigh like a whole pile of carbons, right, 99 of them would weigh 12, one of them weighs 13, and your average is about 12.01. So does that make sense for that?
Yeah, so is that a good way to like check to make sure you did your math right? Is to look on the table?
Sometimes. I want to say yes, like you should be around this like for your total mass, but you'll notice, especially when doing the practices, you might be doing an isotope that's heavier than on there, and you just don't want to let that throw you off. But definitely check your atomic number with the periodic table. So then looking at these neon examples, so let's compare. So neon 20, neon 21, and neon 22. So again, we all know that they have 10 protons. And now how many neutrons will they have? So neon 20 has how many neutrons? So 10, neon 21, 11, and neon 22, 12. And then I'll add in our electron column. So again, these are neutrals, so we don't have any charges over them yet. And so they would all have 10 electrons to match our number of protons. And so again, our isotope representation, you'll see probably different ways to write this, but the mass number should be on top. That should be the big number. Atomic number on bottom should match with your chemical symbol. I'll add that should match symbol, so you can always double check yourself. And then don't forget your mass. So your mass is equal to your protons plus your neutrons. And so that's represented by symbol A. You can write, so mass protons plus neutrons. And so again, just other ways to write it. So you might just see neon 20 or any 20, any sort of combination like that. All right, so let's try this practice. So what are the atomic numbers, the mass numbers, and the symbol of the chlorine isotope with 18 neutrons? We'll give everyone a minute or two to look at their periodic table. Let's see, we went over to our periodic table, looked up chlorine. And so what's the symbol for chlorine? So Cl, and then, so it had 18 neutrons. How many protons does it have? 17. So 17. So what's its mass? 25? So 35, so then I should write 35, 17. And that looks good. So is this what everybody wrote? Excellent. Let's, because I think I always forget, yeah, let's talk about ions before I forget. So ions now are going to be charged atoms. And so they could be positive or negative. And so what we'll find is metals tend to form positive ions. So for example, you might see Na plus like so, and you could write it like that. What else? I'm trying to think. Look at calcium. You could also write, so if I wrote 42 Ca2 plus, that's telling you a bunch of different information, so we'll break that down in a second. You could also find, so that you'll see that nonmetals tend to form negative ions. So you might see like sulfur 2 minus, oxygen, chlorine with a negative charge. And then let's even take this. So you could have this example, 35, 17 chlorine, and then I can stick a negative charge on there, and now we have an ion. And so let's kind of break down what these ions are saying. How do we determine the charge? And so let's